Hi, everybody. I'm really happy to be here. I would thank the organizers for inviting me, but you probably saw that I'm on an organizing committee. And moreover, I think Juan, Nati, Ignacio, and Umesh have done all the work. Maybe the only thing I did was invite myself to give this talk. By the way, that's a good time for everybody to thank the organizers for this wonderful workshop. So, yes, so I want to tell you about proofs. And the value of errors in proofs, which is obviously not what you think. And the subtitle is very long, The Fascinating Journey from Turing's 1936 proof of undecidability to this recent breakthrough, MIP star equal RE, so which is, I think, the main reason physicists, quantum physicists in particular, are interested suddenly in interactive proofs. There are other interactive proofs that have appeared already. Harlow and Hayden suggested more than 10 years ago to explain some of the black hole paradox with zero knowledge proofs. And proof systems, we have a plenty. And in fact, I'm going to give you a survey of the evolution of proof systems within complexity theory, and in particular, proofs that have interaction, randomness, some quantumness, like MIP star, and and errors. Okay, so what's the plan? I'm not in a hurry. Please ask me questions if anything is unclear. That's the plan. I want to tell you about this value of errors in proofs. I will not talk much, but it has a huge impact, huge scientific impact on various scientific disciplines, on crypto and technology in general, conceptual ideas that arose, and on mathematics. Before I tell you about the value of errors in proofs, I will tell you about value of errors in computations. In fact, we'll discuss a lot in the beginning the interplay between computations and proofs that has a very long history. But most of all, I really want to tell you about my field, which is complexity theory, and about its methodology and how it naturally led to this evolution of proof systems, which it focuses on modeling, on classification, or algorithmic efficiency when studying anything. Okay. There's as I said, a long history of interaction between proofs and computations, and even the ancients thought about it. I'll tell you just 2 points in the long history of interaction. One is Euclid's Elements, maybe the first book of mathematics. As everybody knows, it has proofs, a collection of proofs of statements in plane geometry. But if you read all the proofs, but all of them, they all have algorithms in them. They all have algorithms to construct the specific point sets described in the theorem using very simple 2 operations, using a straight edge and using a compass. So it's really a computation. And in fact, in plane geometry, anything you can prove, you can compute the proof. On the other hand, just in the turn of the century, a story everybody knows, Hilbert had a dream. His dream, which he made explicit, is that truth in mathematics is the same as probability in mathematics, and that probability, in fact, can be obtained by a mechanical procedure, by computation. Of course, this dream was shattered. First, Gödel proved his incompleteness theorem, shattering the first equation, and then Turing came and disproved the second part. Not everything provable is computable. I want to talk about Turing's work. Key to Turing's work was actually to define what computation is. And he defined the Turing machine, which is by now accepted as the model for computation, simulated by any other, and can simulate any other, including not just man-made, but computation in nature. This is the same as what algorithms did. You do a simple operation, a sequence of simple operations, and then you stop and declare the output. Of course, this is one byproduct gave us a computer revolution, but I'm not going to talk about that. I'll talk about theory. What are we computing, first of all? For the rest of the talk, we are computing just decision problems. We are given some set, and we want to know whether a given input is in the set or not. Yes, no answers. Okay, or we may be interested in proving that X is in S. These are the problems we face. And then Turing defined two sets. I mean, he didn't really define them, but talked about them. One is everything computable by finite algorithms. And the second, RE, recursively enumerable, is sets which are provable to finite algorithms. We'll talk about the meaning of this, but that's basically the two distinctions we want to have between computation and proofs. And his famous theorem that the halting problem is undecidable can be stated in this way. Halting problem of Turing machines is recursively enumerable, but it's not recursive, so it's an uncomputable problem. Just as an aside, which will come back later, the problem that is the main problem of our field today and of mathematics, central problem, is the P versus NP question, which is exactly the same problem if instead of finite algorithms and finite proofs, finite algorithms, you talk about efficient algorithms, algorithms that will end in our lifetime. And for here, we'll take the definition of polynomial time computations. There are many studies of other notions, but we'll fix this. So this, as you know, is still open. Okay, good. So now we want to talk about proofs. And I'll just run from some examples to, talk about the many notions that we associate with proofs. There are claims, there are arguments, some of them are proofs. What is a proof system? These interaction provers and verifiers. So the setup is, in general, you can think about life, not mathematics. When are you convinced by anybody of anything? So we want to have some claim. S is a fixed set, let's say the prime numbers. X is an input, maybe it's an integer, and you want to know whether it's a prime. Okay, there are two essential parties here. One is a verifier who wants to know, really eager to know whether this is true or not, but is limited, cannot do it by itself, cannot compute it. And on the other hand, a prover that may be infinitely powerful, knows everything, but cannot be trusted. So, the verifier wants to be convinced. And this is usually augmented by an argument that the prover sends the verifier to convince him. Now, I want to give a few examples of proof systems. Some of them are standard. In fact, you've seen one already, plane geometry of Euclid. It's a deductive system from axioms. I want to give you a few that look non-standard, but they are proof systems nonetheless, that prove a variety of families of theorems. Here's the proof system designed to prove only that a number is composite. Here's a claim, a typical claim. This number is composite. What is an argument that should be convincing? These two smaller numbers, so that what is the verification the verifier do? It will multiply these two and see whether it gets the input or not, and accept or reject appropriately. There is a key, a property of all proof systems we'll discuss, is that we want the verification process to be simple, to be efficient. The verifier is limited, right? Here, of course, it's just arithmetic to multiply. This is general. It works not just for this input, but for any input. And what's the set of theorems that this proof system defines? Well, the theorems are those things accepted by the verifier, in this case, all the composite numbers. So it doesn't look like a theorem in mathematics, but it's a theorem. Okay, that's one proof system. I want to stress that we don't care about the difficulty of how complex is it to figure out the argument, how hard the prover has to be or how clever. We don't care about this. In fact, in this particular case, cryptography, or in fact, all of us assume that this is a hard task. We build on it because almost all security systems, which are maybe being replaced right now, but existing ones, explicitly assume that this is a hard task, infeasible, right? So we don't care about this. Proof system is all about the efficiency of the verifier. Either there exists an argument or doesn't. Here's another proof system. It's for Sudoku puzzles. What are the claims? The claim is this Sudoku puzzle is solvable. Of course, not all of them are, even though in the newspaper there are. Not all of them are. And what's an argument for this? Well, a filling of this table using the Sudoku rule. So verification is a very easy process. You just check the Sudoku rule that you have all the numbers in every square and every row and every column, and decide to accept or reject. That, of course, is a very simple, efficient procedure. So this is satisfied. And of course, okay, what are the theorems proved here? It's, the set of all solvable Sudoku puzzles. This is not a finite set, general, because you can think about Sudoku in any size, right? Okay. Here's another proof system that you all know or heard about. This is another deductive proof system like plane geometry. It's piano arithmetic or similar. We have, I don't know, hundreds of them in logic and math. It's a proof system that manipulates objects, in this case, formulas over the integers. Let's call the formulas A, B, and so on. Has a set of axioms, which, are self-evident, like commutativity and, basic things, induction, and so on. I didn't list all of them. And deduction rules. There are ways to get from some formulas to others in a sound way. If we know, for example, we know that A is true, and we know that A implies B is true, we can infer that B is true. Okay, so that's the rules. And what does an argument look like? Let's say for a formula C. Well, it's a list of other formulas, A1 through AM, such that, what the verification doing, it just checks that you are doing only legitimate things. Every AI is either an axiom or it is deduced from previous ones using a legal deduction rule. And again, accepting or rejecting, it's all syntactic, so it's efficient. What's the set of theorems in this proof system? Well, it's more interesting, right? There are infinitely many primes, Fermat's last theorem, and et cetera, et cetera. But it's a proof system like the others. And now that we've seen these examples, any questions? But please feel free to ask questions. We can now look the way complexity theorists look at everything. What is a class containing all proof systems? And this is, what do we want? What's essential in a proof system? Well, two properties, completeness, namely true claims have proofs, and soundness, false claims don't have proofs. This has to be in any proof system. Finally, the efficiency of the verifier is often implicit and not written down, but the proof system is useless if the verifier has to compute some incomputable or inefficient thing. So this is implicit, and I want to make it explicit. Distinguishing these two cases, whether the claim is true or false, whether the argument convincing or not, should be an efficient process. And again, we take polynomial timing. So let's formalize this complexity theoretic view. This was done by Cook and Oreschap. And they just formalized what I said before. So let's say what a proof system is. A proof system is an algorithm. It's an algorithm, call it V for verifier, which takes two inputs. One is a claim, one is an argument. And it should satisfy these two conditions. So if the claim is true, then for some argument, the verifier accepts. Okay, of course, this is a happy case where we call the claim a theorem and we call the proof, the argument a proof. That's a happy case. soundness. If the claim is false, no arguments at all should convince the verifier, it should reject. Given a proof system, namely such an algorithm called TV, setup of proofs in this system, and now it's very easy to just see that the collection of all families of theorems for all proof systems is really the class NP. It's things you can easily convince somebody else with. And we saw examples of these sets. And P, the class P, if you didn't know the definitions, it's just everything that, all the set of theorems you can prove for verifiers that don't look at the argument. Namely, they take the claim and know the answer. So that's another version of the P versus NP question, whether these two classes are the same. Okay, now that we've seen classical proof system, complexity theory enters around the 70s with errors. Error is the main thing in the title. So I want to talk about errors in probabilistic proofs. But before that, I'll just give you a one-slide review of errors in computations. I'm sure you've seen probabilistic algorithms, but I'll just run through this. So what's a probabilistic computation and error? First of all, we assume, it's easy for physicists, whatever natural resource we have, we might as well use in algorithms. So we let algorithms make random choices. And the difference between deterministic and probabilistic is that in a deterministic algorithm, everything is specified. And in particular, we say that an algorithm computes a function if it returns the correct value for every input. On the other hand, in a probabilistic algorithm, the outcome is a random variable. Can be right, can be wrong. We demand that for every input, over the random choices of the algorithm, most of them give the right answer. I said most here, 2/3, namely error 1/3. You may be unhappy with this. We'll talk about this in a second, but I want to say, already here, this is the introduction of error. We allow algorithms to make mistakes with small probability. What do we do if the error is not small enough? This is not a problem, so we can choose whatever number we want there, bigger than a half. If the error is less than a third, and we run the algorithm, let's say, k times and take a majority vote, and decide according to that, then the error drops exponentially. So we can reduce error arbitrarily in probabilistic algorithms. We don't worry about that. Why? What's the value of allowing errors in algorithms? Well, it seems like we can solve many more problems. You all know about Monte Carlo methods, for example. I want to stress that the theme is that we don't know that it's true. We don't know that we need randomness. We cannot do away with randomness. But this is a topic for a different talk that I like to give. I'll leave it aside. What's the rationale for allowing errors besides that? I think we all tolerate uncertainty in life. We cross a street. We are not absolutely sure we'll get to the other side. There's some element of uncertainty there, which we cannot reduce arbitrarily. Anyway, why not in algorithms? So good. So these are errors in algorithms. Now we want to move to errors in proofs. This is really easy, because remember, proof system is an algorithm. So we just introduce randomness into it. Here's the definition of the original proof system. And now in these two papers by Baba and by Goldwasser, Mikhaili, and Rakov in '85, they did this generalization. They said, let the verifier be a probabilistic algorithm, okay? And let it allow error. We just demand these two properties, completeness and soundness, with high probability. We allow a tiny bit of error. Also here, you can reduce error arbitrarily. And now we've done the same. We've introduced errors in proofs. And somehow, psychologically, it seems to be a completely different game. It seems like, beforehand, okay, maybe we're only sure that a number is prime with 99.999 probability. Proofs is something, holy. doing this is sacrilegious. Proofs is what distinguishes math from all other disciplines. So, but this is it. We are doing it, and let's see what comes out. In the same way, we let T sub v be the set of theorems in the system, namely everything is a verifier except with high probability. And the class of all things provable in this type of system is called IP, and I is for interactive. So I didn't tell you the whole story yet. I told you about randomness. I have to tell you about the interaction. So let me do this in the next slide. But anyway, we have a similar class, IP, like we had NP. This is the fuller picture. I remind you that in NP, which is deterministic, and we insist on always correctness, there was an argument that went one-sided from the prover to the verifier, like writing a paper and publishing it. And that was the whole interaction between prover and verifier. On the other hand, in IP, we said now we are probabilistic, we demand everything with high probability, but there is another difference. Namely, we allow the prover and verifier to talk to each other. There is some interaction where, in particular, the verifier can ask questions of the prover. Why did you do this? Give me a full proof of this lemma, whatever. And only then, only after this interaction, which of course is short because the algorithm is efficient, the algorithm decides to accept or reject with high probability as demanded. A good question for this model, for any model that you introduce in any field, whether it's reasonable. Yeah. No, because it's with high probability. So there are these things the verifier accepts with high probability, and these are the theorems. And all the others rejects with high probability. So I just replace 1 and 0 of the deterministic proof systems by 0.999, by 0.999 and 0.001. Yeah, exactly. The same thing. It's uniquely defined, yeah. There's no question of what is a theorem. The proof system guarantees that there is this gap, and you take the theorem. Good. More questions? Okay, so is this reasonable? Well, I mean, just think about it. Of course it's reasonable. In any classroom we teach, or in any interaction working on a problem, we talk with each other, right? It makes sense that there will be interaction, maybe something is unclear and so on. So I claim it's reasonable. Anyway, this is a definition, but still, I think it's reasonable. But far more than that, I want to stress that these papers, change everything. It's a revolutionary scientific notion. You will see as we evolve what it led to, and a little of what it led to, and you'll be convinced of this. But this is like an earth-shattering event, the definition of interactive proof system. Okay, so let me move to talk more about them. And okay, that's a slide saying in more detail what I said. It had huge impact on all these areas of our life, but I am going to focus on how it led to other proof systems. There are many I will not talk about. There are various proof systems in which randomness is public. There are proof systems where you limit the prover, even though the prover is supposed to have unlimited power, which is basically the question of cloud computing or underlies cloud computing. There are many variants I'm not going to talk about. I want to focus on two proof systems which have very paradoxical properties, and I'm sure you heard about them. These are zero knowledge proofs, and the proofs that convey zero information, and PCPs which are probabilistically checkable proofs. These are proofs that are convincing even though you hardly look at them. And I'll explain both. And moreover, I want to talk about actually there is a connection between them, even though they are completely different notions. And this meandering journey also will show you how we got to this very last MIP star kind of proof system that's so popular now. Okay, so let me start with zero knowledge. Okay, so what is a zero knowledge interactive proof? This was already suggested in the original paper of GMR. In fact, one of the motivations, they were coming from cryptography, and they were interested in the following notion, again, zero knowledge interactive proof. First of all, it's an interactive proof as I defined, a probabilistic interactive proof. And you'll demand one more thing. On the side, formally defining it is highly non-trivial, but the intuition of the definition is very simple. It's just what you think. So it's an interactive proof plus the demand that whenever the verifier accepts, namely this becomes a theorem in our proof system, whenever the verifier accepts, it learns absolutely nothing that it didn't know before, except that the claim was true. Okay, it's a definition. It's even clear why it's nice for cryptography to have this definition. Let's say that I, as a user of some public key crypto system, should pick two primes, multiply them, and make it my public key. How do you know that that's what I did? Maybe I multiplied 3 prime numbers, and maybe if I did multiply 3, it ruins the security of the proof system. All right, so you really want to, and of course I don't want to reveal the primes to you because that's my secret key. That's so you can imagine there are many examples why zero knowledge proofs would be useful. Yes. Absolutely, absolutely. Randomness is essential for this. Deterministic interactive proof systems cannot be zero knowledge, and in fact they collapse through NP. Yeah. Okay, so that is demand, and of course, if it's reasonable. I mean, I think for anybody on the streets, and especially to us as mathematicians, it sort of goes against our nature to believe that I can talk to you and be convinced of something I didn't know without you giving me any information. It just sounds impossible at any level. In particular, if somebody comes with a claim of this nature, proving, we'd like to see something. And in fact, mathematics is built not just on its theorems, but on the proofs, which have ideas and proof techniques and so on. So what's going on? Well, which theorems can be proven in zero knowledge? That's what they ask. They give a couple of number theoretic examples, and they ask what else can be proven in zero knowledge. And what we did a year later with Goldreich and Micali proved that everything is provable in zero knowledge. What is everything? Everything you can prove, you can have a mathematical proof for, you can have a classical proof system for, can be proven in an interactive zero knowledge proof. Formally, there is an assumption. It's a very important assumption. It's an assumption that one-way function exists. For the layman, it's simply the assumption that we have cryptography. I can tell you exactly what. But basically, this is the assumption that we use whenever we shop online or whenever we trust any password system. So it's a standard thing that the world accepts, but it's an assumption, and we'll talk about it later. But anyway, anything that has a proof has a zero knowledge proof, can be convincing without revealing anything. This talk, when I didn't realize initially that I have an hour and a half. Juan told me maybe I don't have an hour and a half. At any rate, I prepared slides, or I had slides for proving the zero knowledge theorem. So I actually, in about 10, 15 minutes, I can prove it to you or give you a high-level idea of the proof. How do you do that? How do you convert any proof to a zero-knowledge proof? After I'm done with the talk and you ask me all the questions and we see if we have time, and if one is willing, I can give you the proof of this theorem. Okay, so let me proceed. This is you. Excuse me? I can give you an example of zero-knowledge proof. I will not prove that zero-knowledge, a very famous example that is already in our original paper. It's a proof of graph non-isomorphism. So there are two graphs, and the claim is that they are not isomorphic. This problem is interesting because it seems infeasible. In fact, for decades, we had no even little bit efficient algorithm for it. So it's really interesting if somebody can convince us of that. Okay, let me just say, so everybody understands two graphs. So if I draw this graph, this is really the same graph. I just permuted the pentagon, right? I just permuted the vertices. So these two graphs are isomorphic, but there are some isomorphic pairs and some non-isomorphic pairs. To convince you the two graphs are isomorphic is very easy. It's actually in NP, right? I tell you the permutation that maps, 1 to 1, 2 to 2, 3 to 3, 4 to 4, and 5 to 5. And you can check that all the edges are mapped to edges, and you are happy. Okay? So this is a proof. It's very easy to prove that two graphs are isomorphic. But how do you prove that two graphs are not isomorphic? That there is no isomorphism? You're not going to run through all n factorial permutation, right? So here's the proof, and even proving it, forget zero knowledge, is not obvious. It should not be obvious. It's not difficult once I'll tell you, but it's not obvious. And this proof can be, actually, you'll see that it's essentially zero knowledge. Okay? So how do I prove to you that two graphs so we have here G and H. There are graphs on some set N. So this is also a graph on the same vertex set. They are labeled graphs, right? And I want to prove to Pierre, I want to prove to Pierre that they are not isomorphic. So what I do, we both know these graphs. I pick a random permutation on the letters, on the names of the vertices, and I send Pierre, I wish I had a space here, and so the prover sends the verifier either, or I maybe pick two random permutation. I send to Pierre either sigma of G or pi of G. Okay? Sorry, the verifier. Just flip them. The verifier is testing the prover, wanting to. So Pierre tells me, did I send you pi of H, pi of G, or sigma of G? And maybe let me change it a bit. Let me say that Pierre is sending me either let's say one permutation, send me either pi of G or pi of H. And ask me, did I send you pi of G or pi of H? Now, if the graphs are not isomorphic, then these distributions are disjoint, and I am all-powerful, and I tell you which one you chose. And the point is that if the graphs are isomorphic, these two distributions are identical. So there's no way for me, being all-powerful and everything, there's no way for me to distinguish. So I say something, and I have probably a half of error, which we can amplify. This is a proof system in interactive proof. Moreover, you can see that in the case that the claim is true, they are non-isomorphic. What did you learn? You learned whether you send me H or G, but you know that. So it's zero knowledge. Formally, to prove that zero knowledge is more interesting, but I'm not going to get into the subtleties there. But essentially, notice here, cryptography is not used. This is a stronger claim. Here, there is a zero knowledge proof of the theorem, which does not use cryptography. But for the general theorem, you do need cryptography. Okay? So this was a detour, was an example. Thanks. It actually was very good to do that. So as I said, zero knowledge had lots of impacts. This theorem has theoretical impacts. It really underlies a general mechanism to transfer any protocol for many parties which trust each other and never cheat into a protocol that can go between people who don't trust each other and are cheating. Basically because everybody will need to prove in zero knowledge that they are doing what they are doing, and so it will be convincing, only they will never reveal their secret. There are many practical applications. To my amazement, the proof of this, the formal proof, was simplified enough, maybe under more assumptions, to actually be embedded in lots of real security systems that you know about. It was generalized in amazing ways. For example, this physical zero knowledge proof. It was used in a proposal for nuclear disarmament. It was used for police work, anonymous DNA testing, and so on. Not going into there at all, because I'm talking about proof systems. So let me tell you how this led into even more proof systems that we mentioned, and in particular the multiple prover interactive proofs, MIP. Okay? So here's how this happened. It's very bizarre. Remember, I told you the zero knowledge theorem. I told you that we need an assumption, namely cryptographic assumption that one-way functions exist. By the way, the definition, I'm sure many people have seen it. The definition of one-way function is very simple. It's a function that is easy to compute in one direction and hard to compute in the reverse. We saw one, multiplication of integers is easy to do, but factoring seems hard. So you should believe that one-way functions exist. Anyway, there is an assumption here, and again, complexity theory always insists on minimizing assumptions, and we asked ourselves whether this was essential. It's a one-way implication. And the answer, as always, or as many times, is whether cryptography is necessary, is yes and no. So in what sense is it yes? Well, Ostrowski and I proved that in the IP model, in this model of interactive proofs, if you can make any proof zero knowledge, then there must exist one-way function. So yes, it's essential. But why is it not essential? Well, again, like happens a lot in mathematics, we change the model. So we change the model. So this is a paper a few years later with Benoit, Goldwasser, and Kilian, in which we changed the model. How did we change it? We allowed more provers. The more, the merrier. So the new proof system, new type of proof system, I'll talk about 2IP, namely with 2 provers, but you can imagine you can have one with 3 or 100 or n. Okay, so 2 provers now want to convince a verifier of a claim. How does this happen? So the provers can meet beforehand, even knowing the claim, discuss whatever strategy they want, but then they are separated, and then the verifier can interrogate them independently. After he starts asking questions, they are not allowed to communicate. Okay, so the model is clear. And of course, after this, it decides again to accept or reject with high probability. And we proved that in this model with two provers, you don't need cryptography. Every proof can be made a zero-knowledge proof without any assumption. So that's very nice. It's one motivation for this class MIP. It allows zero-knowledge proofs without any assumptions. In some sense, physical separation of the provers replaces the need for cryptography in this model. And you can ask, like we asked before, is it reasonable? Well, I have two answers. One is it's reasonable in real life. We know police likes to, when catching two suspects in the same crime, they would put them in different cells and interrogate them separately. So it, in some sense, happens in life. Another, not a proof, in fact, but a story is that when we came up with this result, the institutions we were at, the Hebrew University and MIT, insisted on patenting it. So that may make it reasonable. I don't know. I can tell you that against our will, they did patent it. And of course, it didn't make a sense. Although today it might have been different. The idea was that you come with two cash cards to two machines that are separated by a lead wall, whatever. Anyway, you can imagine, you can at least imagine, or some people imagine that it can be useful. And then at least I was happy. I mean, we understood what we wanted to understand about zero knowledge, and I personally sort of left this area of interactive proofs. And just then, everything happened. So let me tell you what happened. We were in this situation. I defined for you more and more general classes of proof systems, obviously containing each other. And we said we are interested in the relationship between proof and computations. What is the power of the new proof systems? Can they prove anything more than NP? Well, you know, what's the maximum they can prove? And people very easily show that maybe you don't like computer science acronyms, but basically they show that if you have a problem provable in NP, a set provable in NP, then it also can be computed in polynomial space. Polynomial space can be exponential time, but still, it's a limited class. Things computed by many prover interactive proofs are also limited. They have to live within non-deterministic exponential time. Anyway, these were believed to be very generous inclusions. And nevertheless, really a couple of years later, we had a complete understanding of the power of these proof systems. In fact, these upper bounds turned out to be exact. IP equals P space, can prove anything in polynomial space. 2IP can prove anything in non-deterministic exponential time. And then there's the PCP theorem I'll tell you about in a second. But not only did we understand, you know, in acronyms what they meant, each of these theorems have a strong conceptual meaning. I mean, IP equal P space means you can prove not only statements of the form there exists something like NP. It can prove optimality of strategies in games. It can capture, polynomial space captures things for any move I make. You know, here's the move I make. For any move you make, I have another move. For any response, I have another move and I win. So many alternations. This is still doable only in the context of interactive proof. The many IP equal non-deterministic exponential time means we can prove to efficient algorithms things that are not efficiently computable, right? Non-deterministic exponential time is stronger than non-deterministic polynomial time, in particular, stronger than polynomial time. So things that cannot be computed efficiently at all are provable in this system. These are very strong systems, a very strong statement, and intuitively meaningful statement. And then people took the second result and scaled it down and did lots of other wonders. This combined two papers from about 92 gave us probabilistically checkable proofs, which is another characterization of NP, extremely non-trivial characterization. Basically, it says that reason proofs can be verified from constant size snapshots, and let me make it more explicit. By the way, in all these are theorems in the normal mathematical sense, that they don't know hidden assumptions, no cryptography, nothing. So I want to tell you about TCPs. So what are probabilistically checkable proofs? First of all, they are non-interactive proofs. They are like NP. The prover only sends a message to the verifier. So it's a probabilistic proof system. There's still randomness here, but only one directional message or just a paper being published. Besides being interactive proof, you demand, there's a limitation on the verifier. The verifier doesn't matter how long the argument is allowed to look at only 20 bits, maybe 20 random bits of this very long message and decide accordingly, and still be correct with high probability. Just, just like before, it seems ridiculous, counterintuitive. How do you find a bug in a 100-page proof? And one way to imagine, I don't know what Wiles is doing nowadays, but maybe he's working on the Riemann hypothesis. Anyway, he may produce at the end some huge, volume, and publishes it, right? Writes it down, and we need to check it. How do we find if there's a bug? I remind you that in the original proof of Fermat, there was a bug, and somebody found it, but whoever found it read the whole thing. Well, it seems impossible, but like before, it's not only possible, it's universal. Every proof, every mathematical proof can be converted efficiently into a PCP, namely a proof that can be checked with high probability correctly by simply sampling, let's say, 20 bits, some constant number of bits. The constant just tells you what error you get, what is the error. You can read 5 bits and get maybe error 1/3, or you can read 20 and get it to be 1%, and then maybe you read 100 and it's 1 in a million. So that's a statement. What are the implications? Well, the obvious implication, which still wasn't, I think, made feasible, is that that's what we would love as mathematicians, to get a paper to look at 20 bits and decide whether it's correct or not. But referring is still not an application out there. It really had amazing applications in complexity theory, in coding theory, and maybe the most important one in optimization. We can finally use this statement to argue things we didn't know before. Before, with NP-completeness, we could argue about hardness of computing optimal solutions to optimization problems. This allows you to compute, to prove that it is hard even to approximate the optimal solution to an optimization problem. It's a whole world there. Anyone interested, we just hired Irit Dinu, who is here in the audience. You can ask her plenty of questions about this. It's one of her specialties. And as I said, again, things like this have been implemented and are essential in many security systems. Okay, good. Questions? Yeah.
I think of NP as a deterministic class. So why should it be equal to something involving probability? I guess I know we think
we changed two things. We demanded a lot of the verifier, but we allowed it to have error. In NP, there is no error. So we made it both stronger and weaker, and they turned out to be equal. I mean, the question is good, but to tell you why it works, I need to show you the proof. The original proof is quite complex and algebraic, it's heavy. And some decades later, Irit Dinu gave a very different proof, very combinatorial. That's much easier to understand and also give more efficient parameters. If you want just an analogy to see why is it even possible, for those with some intuition about error correcting codes, imagine the coding theoretic problem in which I encode a message in some error correcting code, and I send the encoding, and we know that if it's a good code, even if there are many errors, the verifier should, or whoever the receiver can figure out what I sent. That's a normal error correcting code. But assume, and this is a problem that actually came from this study, that you only are interested in one bit of my message. You really want to know if I love you or not, right? It's the whole story, just one bit. Can you figure out what's the value of this bit? Not reading the whole, 1,000 bits I sent you, but reading 10. So it's an analogous question, and this is called local decoding. And at least in the coding theoretic world, you can maybe more believe that it's doable. Okay, maybe. Anyway, it's an analogy to finding a bug in lots of, in a sea of proof. So that's.
Maybe I made a probabilistic version of NP.
Yeah.
So I said, rather than I have to be able to verify with the probability 1, I just want to be able to verify with some.
It's a very good question. If you just let the prover send the message, and then you let the verifier be probabilistic and check with high probability, you don't change NP.
I think so, it takes the same class.
It's the same class.
That's a provable thing.
Yeah.
Because I know if P equals BPP, it's not provable.
No.
When you say within.
The other is not provable. It's saying that everything you can prove efficiently, you can compute by probabilistic algorithm. We don't believe that you can. Yeah, I mean, P different than NP and BPP different than NP are essentially the same statement.
Yeah.
So it's a different, yeah.
P is supposed to be equal to BPP, but we can't prove it, right?
Yeah, we believe it. Actually, it's true if. No. This is a very different statement. This is it's not, BPP is not really involved here. Here's a verifier that is probabilistic. It's, the verifier gets something, whereas in a BPP algorithm, whoever computes gets nothing. So the existence of a prover is central. So it's a different type of question. Okay, and it's provable also. Okay, more questions. Okay, let me go to my last part of the lecture, which is about quantum proof systems. So we have this characterization, this wonderful results. We understand probabilistic proof systems. And now we are going to go to quantum proof systems. One, like I did with the randomized algorithms, I'll tell you one slide about quantum algorithms. I'm sure many people know about this, but here's the slide. As before, nature seems to provide us with quantum phenomena. And why not use it in algorithms? This was the suggestion of Manin and Feynman in the early 80s, suggested that we build computers with rules of quantum mechanics. We have it, right? With quantum mechanical parts, in particular, they can manipulate superpositions using unitary operations. Very different than normal Turing machines. Why not? Okay. So formalizing it and formalizing what is efficient algorithms, what's called BQP, P is for polynomial time again, what quantum computers or quantum Turing machines can do efficiently. It took time, it's non-trivial, it's much less trivial than, let's say, randomized algorithm. It's very easy to show that they are at least as powerful as probabilistic algorithms. Basically, you measure everything in the beginning, so you generate all your randomness. But anyway, they are at least as efficient, and there were some initial attempts to understand the power of this model. And then, a volcano erupted, and Peter Shaw proved this theorem that both factoring and discrete logarithm have efficient quantum algorithms. And why was it a volcano? You know, because everybody went berserk. There were friendly attempts to do everything, to build supporting technology, to build quantum computers, right? It's a theoretical model, let's build it. This, as you know, billions are invested. We've been at it for 40 years. Technology improves tremendously, but we still cannot factor, maybe we can factor 65. Other things are doable. I'm not belittling it at all. It's amazing what's going on there. Friendly attempts to protect from such computers, right? To build a post-quantum cryptography, because these problems, factoring in discrete logarithms, underlie current security system. If there are quantum computers, we cannot use them. So, in fact, there are really nice suggestions. So, mainly problems that are based on lattice problems that currently we don't know quantum algorithms for, and people are actually replacing security systems more and more in the world by systems based on these lattice problems and so on. Of course, there were attempts to explore further the power of these quantum algorithms, and I must say, we don't have many more different methods than what in Shor's algorithm. It's basically the ability to do exponential size Fourier transform over a billion groups. But what we can do, what we are good at, is invent new models. So we don't have quantum algorithms yet, but why not think about quantum proof systems? And we do. So people started suggesting quantum proof system. You know, they verify the quantum algorithms, the provers, they are infinitely powerful, they can do also quantum operations. What was proposed and formally defined, these things are a bit tricky. Define IP star, so whenever you see a star, it means that it's a quantum proof system, the analog of its classical one. And it took about a decade to prove that it adds no power to interactive proofs, to one prover interactive proof. It's highly non-trivial, but they cannot do more than p-space, like classical. Okay, so that was a nice story. And then in this paper, a few years afterwards, they defined the analog of multi-prover interaction proofs, MIP star, and people started exploring the power of this. It took time even to prove that they are stronger than the classical ones, because you add power both to the prover and to the verifier, to the provers and to the verifier. So even this is not trivial to show that it's at least as strong as the classical one. And people believed, you know, okay, more work that proves the equality and we can go home. But as you know, this was not the story. A few years later, and with a lot of techniques from both quantum computing and from classical interactive proofs and coding theory, Sarjan on the right shows that actually you can do more. You can do double exponential time. So this was source of shattering, and now we really have to understand what this weird proof systems can do. And the famous theorem from a few years ago was that, I still read it and I still don't believe it. MIP star equals RE. RE is the class we saw in the beginning. It's the class defined by the halting problem, undecidable problem. Undecidable problem statements can be proven to an efficient quantum verifier. This is from a complexity theoretic standpoint, computability theoretic standpoint, sort of amazing. Doesn't make sense, and you might think, okay, so there are 5 letters there, and they have some meaning, and complexity theorists understood something, and they are happy. What is amazing about this result, again, as many of you know, is that it has amazing implications in fields unrelated to complexity theory. So this result immediately supplied counterexamples. These are all in the original paper. It supplied an answer to Tilson problem. It disproves the very famous and the problem that mathematicians worked on for decades, the Korn's embedding conjecture. He believed that, certain, well, I won't talk about it, but anyway, disproved it. And in group theory, and there are other variants, they're all related, in fact, in some sense equivalent formulations of this problem, but even this took time to discover, and they exist in very different areas. MIP star equal RE implies, the resolution of these questions or conjecture. This is pretty amazing. I'm not going to go into any of this. I just want to tell you a little bit about MIP star and how it's related to physics from the beginning. Questions? So even when they were introduced, MIP star in this paper, they already know and told you about, told the readers about its connection to foundations of quantum mechanics, to the EPR controversy, to Bell inequality. So I'll tell you about this power of entanglement. Early on in the history of proof systems, this paper showed that when you have more than one prover, you don't need many rounds of interaction between verifier and prover. One round suffices. The verifier asks one question of each prover, gets one answer, and decides. And you don't even need the claim, because whether the verifier accepts or not, this what distinguishes, that's the verifier procedure defines the claim. So you really can talk about a game, and the value of a game, which is defined by the verifier procedure. It's an algorithm that takes 4 inputs, the questions and the answers, and decides whether to accept or reject. And you can wonder, what is the maximum probability that the provers can convince the verifier to accept? This is a classical two-prover system. What happens? It's actually very easy to see that if you give the two provers, even though they are separated, a common shared random string, nothing changes in the value. So let's do that. What happens with 2IP star? It's the same story, only they're all quantum. And now what do you give the two provers? Of course, you give them a quantum state to share, right? Replacing the random string. Now they are entangled. And you will define value star is the best probability that two quantum provers can convince a quantum verifier. And now the complexity theoretic statements I told you, talk about how hard is it to, what's the complexity class I capture? What's a complexity class of distinguishing whether the verifier accepts or rejects, right? To approximate the acceptance probability, the value, with a constant factor. And we know that in the classical cases, an X, when here it's RE, those are the statements I showed. But if you just squint in this description of classical and the quantum prover proof systems, you see something you know. This is, the famous EPR experiment. So it was done here 100 years ago, about the same time Turing wrote his paper. Einstein, Podolsky, and Rosen famously, challenged quantum mechanics and talk about this two-photon experiment. And you see sort of two provers there, the detectors. And I'm sure you know this story. But in fact, they talked about these two scenarios. They called this one a quantum non-local game, or people called it. Einstein talks about spooky action at the distance, how this entangled state seemingly allows to get information faster than the speed of light. And one suggestion was that it has a classical explanation, the above one. He talks about, classical local game where this random variable which is shared is what they called hidden variables. And here, the attempts were mainly not characterize all games, but rather find examples of games which separate the two, where with quantum entanglement, you can do more than with hidden variables, classical hidden variables. And of course, again, famously Bell and then many others looked at a variety of games you know about. I think there were lectures here about specific games where the value star is bigger than the value, namely quantum mechanics was validated, at least at this level. There are things you can do with quantum mechanics that you cannot do classically. This was a theorem, but also it was tested. It was tested physically. So that was the physics side. In the computer science side, already in the original paper, what these people suggested is let's understand all non-local games. Build a complexity theory for this class, like we built for MIP, and understand what's the computational power of this. And I think the sequence of papers that finally arrived at the, this solution, MIP star equal RE, really builds on a lot of the, methodology of computational complexity used previous, as I said, previous results on PCPs, on MIPs and coding theory, and still it's 200 pages. But anyway, we have this understanding, and further we have the implications that I mentioned. In fact, these implications are coming out again. There's just a month ago, the so-called Aldous-Lyons conjecture in probability theory was resolved using quantum interactive proofs, different ones than this, and so on. So let me conclude. We saw lots of proof systems. We saw that allowing interaction, randomness, error, quantumness can give you amazing properties. In many cases, there's all these implications to cloud computing, crypto, Bitcoin, blockchains and so on started before the applications existed. This theory came first. There are amazing connections revealed between subdisciplines here, math, physics, and computer science. And I said it enough times. I think the methodology that is used caused this evolution, and yeah, I think it's wonderful. So if you want to read more about computational complexity, I wrote this book, which is really written as an invitation, and it can be read by anybody, and you don't have to buy it. It's free online on my website. Thank you.
Yeah. How do you formulate something like deduction for a probabilistic proof system?
You don't. As I showed you, deductive proof systems fall even under NP. So that, if the verifier can check something, then it's an NP. So deductive rules, syntactic, which are, as they are in all proof systems, in all logic books, they are automatically an NP. So it's a much more general and computational approach to proof systems.
Yeah. I guess I have two questions related to that. So one is why we don't currently referee papers in seconds. And the other is that, and maybe it's the answer to the first question, is that usually when you read a proof, it's not just because you want to know whether the statement is true. You want to get ideas so that you can prove other things.
Yeah, so both questions are, of course, good. The first question, why we don't see referees in seconds, is because nobody implemented this transformation from a proof to a PCP. And the reason why not, because let's look at your last paper. Is it written in formal mathematics or you use English words? You need the proof initially to be written in piano arithmetic, let's say, or in some formal system. And then an algorithm can, I don't think it was written, but it can produce a proof system. PCP theorem actually gives only quasi-logarithmic blow-up. So if you have a proof of size n, you'll get another proof, a PCP of size maybe n log squared n, not much longer. But this n may be a million or billion if we wrote it, and somebody has to go through the trouble of doing it. I think for concrete proofs you can do it, but then it's not theorems you want to check. To your second question, I managed to forget it.
Saying that you don't just read the proof to.
We care, we as people, as mathematicians, care about learning from proofs. True, and that's why when we write proofs, we insist on providing all this intuition and explaining proof techniques and so on. Other people, like cryptographers, are interested in zero-knowledge proofs. So it depends where you come from. Both are useful. Mathematics definitely use the one where we understand proofs. Cryptography uses ones where we learn nothing from proofs. Depends what you object with. You can do both. Yeah.
If I understand correctly, this result of MIP star equal to RE requires that the two provers share a state which is entangled in a way that is stronger than what.
No, it uses just the usual 0, 0 plus 1, 1.
Be done with 0, 0 plus 1, 1. So they thought that I think it requires that the von Neumann algebras of the observables from the two sides.
Yeah, maybe you're right, it's not 0, 0 plus 1, 1, but it's a simple, finite, the non-local game is simple to describe. Maybe it needs 20 bits. The local game which is used in the theorem.
If I understood correctly, it cannot be represented in a state where these operators are finite matrices or even limits of finite matrices.
No, it is. Well, but maybe our understanding is different, and I am certainly not the expert.
An expert here.
Who's an expert here? Well, I think that Henry Ewan was here in the beginning of the conference, but he's not here. Here, Umi.
The amount of entanglement requires grows unbounded.
So very good, very good. No, yeah, it's not the type of entanglement. I'm sorry. One can wonder. I now understand your question better. Thanks so much. One can wonder how can you prove something with, like an undecidable problem, where the main problem is, how do you know when this machine stops? The time can go on arbitrarily high. That's why halting problem is undecidable. The analog of the unbounded amount of time is the no bound exists on the dimension of the Hilbert space in which the proofs are generated. This is it. But I don't think
finite, right? Some finite dimensional matrix.
This is well, okay. So again, technically, I think it's important what you mean. I think you mean is that this is how the Korn's embedding conjecture is disproved. There is no one formulation of this conjecture. Maybe Pierre can say more. Is that you cannot approximate certain type of infinite dimension von Neumann algebras by a limit of finite ones. Yeah, but I think that the description of the proof systems, in particular the entanglement that gives you these proof systems, is simple.
The reason I'm making this point is that it's not so clear. So you had a statement that nature provides to us the quantum. And it's not clear to me that nature provides the kind of quantum physics that enables MIT. That's the matter.
It's a very good comment, and I cannot defend it because I don't know. More questions? Yeah.
I have an extremely vague question, but do you imagine that one could, in some sense, build probability theory of the axioms of mathematics?
I didn't suggest this. I mean, there are complexity classes in which you have not random errors. There are no random errors. I didn't talk about random errors. I talked about errors in probabilistic algorithms, the usual notion, right? So you want, whoever a verifier or an algorithm is allowed to make random choices. And then you want for every input or for every claim, you want for each of them that it either accepts with high probability or rejects with high probability. There is a gap between the two. That's the world. That's the normal world of probabilistic algorithm. You can distinguish correct things from incorrect things with high probability. Yeah. So that's what you meant, or I?
Well, we meant would you make further clarify?
Okay, so that's something what's that. More. Yeah, so.
I may have another question, but I think you answered this, but I want to. So when you have this interactive provers, why do you need the probability? So if you didn't have the probability and it had to be deterministic, what happens?
You collapse randomly. You can see why, because the interaction is not needed because the prover or the provers will know what the verifier will ask, and so they can condense the whole interaction to one message, right? If you know what the whole point about probabilistic proof systems is that provers don't know what the verifier wants to know. In the example I gave you of the graph non-isomorphism, just imagine it in a deterministic way, okay? If you know I'm going to pick G and or H, right? The provers know the verifier algorithm. The only thing they don't know is the coin tosses. I'll tell you something amazing, the theorem of Goldwasser and Sipser. Think of this graph non-isomorphism problem. It seems absolutely critical that the verifier, I guess Pierre will choose G or H secretly, and will send either the permutation of G or the permutation of H, right? If I knew what he was going to flip, I would know what to answer. The statement, the theorem of Goldwasser and Sipser, says that, think of another proof system in which all the coin tosses of the verifier are known. They are in the sky. They are known to both the verifier and the prover. Still, you can prove graph non-isomorphism in this case. So there's a different protocol. I'm not telling you what it is. It's non-trivial, but you can think about it. Think how you would prove, without any privacy of the random coins. So there are a lot of mysterious things there. Any more questions? Okay, good. So I think, I'll show you the proof of the theorem in another time.
Okay, thank you very much. Let's thank Avi again.